So if you look at this example, we have the dependent variable that is number of marital affairs reported in the last years. So it's the reported number of marital affairs. And we have the... I'm assuming some measurement error. We're going to... OK. So we have the covariates having children, marital happiness, religiosity, and years married as things that might explain the number of marital affairs. And we have a sample size of 600 here. So we can look at this plot here, where we have the count, the different counts on the x-axis, and the dotted line or the dashed line here is the observed proportion of each count. So the first here is simply the number of individuals that had a 0 marital affairs count divided by 601. So 75% of the sample reported 0 marital affairs. And you can see there's a huge drop then to 1, where we have around, I guess, 10% or even below that. And the solid line here is the predicted probability from a Poisson model for the same count. So if you would fit a Poisson model to this data, the model would predict that we would have around 40% 0 marital affairs. So this plot kind of shows the problem of fitting a Poisson model to zero-inflated data. You can think about it if you're used to regression, like fitting a linear regression to a nonlinear relation or something. We'll just fit the data bad, so it won't tell us much about it either. So how can we handle this? Well, we're going to start by actually doing a Poisson model, which we can assume from this fit plot here will not fit that well. But we will try that, and then we'll try other solutions. So to fit a Poisson model, which is a count regression really, the only thing you have to do is you have to specify that the outcome variable is not longer a continuous normal distributed variable. The outcome variable, the dependent variable, is a count. And this goes for anything. If the variable is not a continuous normal variable, then we have to specify for Mplus what it is, what it follows. So in this case, we say count equals n affairs. So the variable n affairs is a count-dependent variable. And actually, we could write within parentheses p, but that's the default Poisson. So you don't have to write, Mplus is known for the default, so we could just, it's an implicit p within parentheses. But we're going to change that in the following input. So I just wanted to show you that there is an implicit p here. So that's kind of everything you have to do to do count regression. And then in the model command, we simply then say n affairs on some variables, and you don't have to say anything about that this is a count regression now, because you have specified that this is a count variable. And we have the covariates here, kids dash years married 6. What is that? Well, a dash implies a list. And to make sense of this list, we have to go back to the use variables option. So if we look at the use variables option, we see they have the outcome variable n affairs, and then we have kids, and then a lot of covariates up until years married 6. So if we say kids dash years married 6, that will imply all the variables between these two. So essentially, this means regress n affairs with a count regression on all the covariates we have on the use variables list. So it's just a short way of writing that. And then we can ask for, we can specify the estimator. Like Bengt said, we will use ML here, and for plots. And if you wanted to have a random intercept for this model, as Bengt talked about, which you can want to have for several reasons. It might make sense, but also to introduce kind of an error term, because there is no error term to the Poisson model by default. You could just add a factor. So you say f by n affairs in addition to the count regression. So you add a factor behind n affairs, and the only new parameter you will have is the residual variance of that one. So a residual variance. All right, so that was the Poisson model. But as we could see from the plot, it didn't seem to fit the data well. So how can we try to do something about this? So the first thing we'll try out is the negative binomial model. And as Bengt just said, what we do essentially is that we add a dispersion parameter, allowing for the Poisson model essentially to have different mean and variance, right? So if this dispersion parameter is equal to 0, like Bengt said, we will have the Poisson model. But if it's larger than 0, then the negative binomial model will shift some probability to the lower counts. And if we go back to the plot here, that's exactly what we want. We want to shift some of this probability to the lower count here, right? We want to move some probability mass. So we can do that just by saying NB, negative binomial within parentheses. That will add this dispersion parameter. We could also add inflation here, like Bengt said. We could not, maybe it's not enough to just shift some probability. Maybe we also have to add this mixture at 0. Think about the 0 as two different kinds of 0. The ones who never drink and the ones who actually drink but didn't drink during this 30 days, last 30 days. And that can easily be done by adding an I, negative binomial inflated. So what we'll have to add then is the model for the probability of being in this never drinking class. So the probability of being in the 0 class here. So that will be, the first is the count regression, and then we have to specify this regression. So you have this number or hashtag, depending on what generation you are in, 1 referring to the latent class of being at the lowest value, being a never drinker, sorry, 0 drinker. And you have, we will use the same model here now for simplicity. But you could in principle have other variables in this model. And of course, you could also, like Bengt said, add the inflation to the Poisson model. If you think that it would be enough to just model the inflation, to model the 0 as a mixture, you could add an I after P, so Poisson inflated. All right, so now we have many models, but I will try to summarize in a bit. But let's just look at the outputs you get from a count model. There's some outputs that you get by default when you do a count model that you don't get from usual regressions. So this table is something that you get, and this is a really nice summary. So what you see here is the count proportion of 0, minimum, and maximum values. So you should read this as the dependent count variable NFRs has a proportion of 0, 75, or 75% of the sample reported 0, marital affairs in this case. The lowest value was 0, which is reasonable for a count variable, and the highest value was 12. So this kind of gives you an idea if this is reasonable to model as a count model. If you only have from 0 to 3, then it might be good with an ordinal variable, ordinal model. And if you have 200 here, then it might be able to use a continuous model. So in addition to this, of course, you get the log likelihood, you get parameter estimates, standard errors, the Z scores, and the p-values. You can also get plots of observed proportion estimated probabilities, and that's exactly what we saw. You can get them in 2 ways. Not conditioning on any covariates, so that's just averaging over all individuals. That's exactly what we saw. We could also condition on covariates, so then you could choose for what values of different covariates you want to see this plot. So this is the this plot for the negative binomial model. So we have the observed proportion and the estimated probability from the negative binomial model. And you can see, you should compare this to slide 25, then the previous plot. I'm not going to flip back, but the previous plot, the similar plot. You can see that the model is much more able to account for this massive amount of zeros, right? So just by moving some probability mass to 0, just by allowing for dispersion, difference between the mean and the variance in the Poisson model, we can capture this a lot better. So you only have to change one letter in the syntax to get this much better fit. Seems worth it, I guess. And this is the output. So we have 2 outputs here, actually. So this is the output for the Poisson regression, and this is for the negative binomial one. So even though we know now that from the plot we saw that the negative binomial probably fits the data best, let's just look at it. We see that we have, for example, very happy. If you're very happy in your relationship, in your marriage, that decreases the count. And it's a significant effect because the Z score is larger than 2 or larger than 1.96 absolute values. And we can see here that everything is significant here, and you have very small standard errors if we compare to these ones where not everyone is significant and you have larger standard errors. And this is something that you see commonly, even if the negative binomial model fits better. Even if you have a significant dispersion parameter, you usually see this. So a good idea is to try the negative binomial model in any case and see if the dispersion parameter is significant, and compare the plots of the fitted and the estimated probabilities. So we can see here that they agree on the very happy variable. It's still significant here, and the estimate is very similar, but some other variables are very off and go from significant to non-significant. For example, years married 3 is significant for the Poisson model, but not for the negative binomial model. And in this case, we would probably trust the negative binomial model more, given the fit. And then we have the negative binomial inflated, or the 0 inflated negative binomial model, where we have 2 regressions, but in the same model now. So we have first the count equation, but then we have the inflation equation, right? Because now we model the probability of being in the never drinker class as well. And this is interesting. If we look at very happy again, very happy in your marriage, you see that it has a negative effect on the count, and a positive effect on the inflation equation. So different signs there. Does that make sense if you think about it for a while? Well, actually it does, because what we model here is we see here is the negative effect. So if you're very happy, that lowers your count, but it increases the probability of being in the 0 class, right? So that's reasonable. If you're very happy, that increases your probability of never having any marital affairs, and it also lowers your count of marital affairs in general. So it has the same kind of effect, but with different signs here, because we're modeling different things. One, we model the count, and the second, we model the probability of being a never marital affair, or however you say that. And as you can see here, the dispersion parameter, sorry, I should say that in the previous plot here, the dispersion parameter was in the heading. Sorry, I should have mentioned that. And it's a significant dispersion parameter for the negative binomial one. It couldn't fit in the table here, so it's a significant dispersion parameter. So the mean and the variance is not the same here. So it's not reasonable to assume the Poisson model, which we could expect given how much better it fitted the data. But I just want to say here that even when we add this inflation equation modeling the 0s mixtures, the dispersion parameter is still significant. So the SIP model here kind of suggests that it's not enough to model the 0s as a mixture. You also have to shift some probability for the count equation to the lower counts. So you kind of need to, in this case, take into account in both ways. And then, of course, you can compare these models. And we're going to use now, since they have different number of parameters, we have to kind of focus on the BIC rather than the log likelihood to take that into account, like Bengt showed you. And as you can see, and now again, the lowest BIC is the best, so to speak. And as you can see, the negative binomial one has the lowest BIC, right? So, and followed by the zero-inflated negative binomial one, which we just saw, and the two-part hurdle, which we didn't look at the output for, or the input, actually. But it's kind of similar where we modeled as two parts. So we might want to stick to the negative binomial one here, but we could actually, maybe from substantive reasoning, stay with the zero-inflated negative binomial model or the two-part model, because we get more information, right? As you can see, we get more information about the processes. We get kind of a more elaborated story about this, which might be very useful. And of course, the choice of which model you use should be based on some kind of substantive theoretical reasoning, right? Does it make sense to model the 0 as a mixture? Well, and if it doesn't, then maybe we should stick with the negative binomial. But if it makes sense and it gives us a lot of insights, and we have this significant dispersion parameter still, then maybe we should stick with the inflated model. And with that, I think, if you don't have anything to add, Bengt, I think you're up again.
Thank you.
And just a little, I'll stand on this side just to vary things. Also because I'm left-handed and he's right-handed. There's a dissimilarity there. So if you look at this, the inflated models here, they have a lot more parameters than the non-inflated. And why? Well, because we regress the inflation probability or the latent class variable onto x variables, and there are many x variables. So the whole extra set of x variable coefficients related to the inflation that comes in here. Now, I actually played around with these data the other day, just I had nothing to do. So, and it turns out if you don't have your inflation part model, you know, the probability of being in the 0 class or not, doesn't have to be regressed on the x variables. It can be just a constant. It doesn't have to vary with x's if you don't want to. And then, in fact, I think I beat most of these BICs. I came down very low here. But of course, BIC is not everything in life. For us it is, but it's then a matter of, well, Morten showed you that many of the inflation regression coefficients were significant. So it's sort of, you miss the story of significant influences on the being in the 0 class if you do what I did, namely get rid of them. But I just want to mention that you don't have to have x's for the inflation part. This comes into play also in growth modeling, where you don't have to have a growth model for the inflation part.